Hi everyone, I'm Kirtika Kanagaraj and I'll be presenting AI Climate Policy Analyzer using Retrieval-Augmented Generation. This project builds an AI assistant that can read complex climate, finance, and policy PDFs and answer questions grounded in those documents. I'll walk through the problem, the RAG architecture, the offline and online components, and then wrap up with limitations and future work. So coming to the challenge of navigating climate policy. So climate policy and policy documents are notoriously painful to work with. First, they are long and complex. A single submission can be dozens of pages of dense technical language, and practitioners usually work with many such PDFs at once. Second, the process is slow and error prone. If someone needs to answer a specific question like how much adaptation finance is pledged under a certain mechanism, they often have to manually search across multiple PDFs, scrolling and using Ctrl plus F, which is easy to misinterpret or miscontext. Finally, the questions themselves are subtle. Practitioners care about topics like adaptation, finance, loss and damage funding, or specific financing mechanisms, and they need answers that are not only quick but traceable back to the original source. So, the core challenge is how can we make these climate policy documents searchable, structured, and queryable in a reliable way. So that's where my proposed solution comes in, the AI-powered policy analysis. The proposed solution is an AI-powered policy analyzer that works as a document-grounded assistant. So it has three main ideas. First, it collects PDFs automatically from the UN FFD4 page rather than relying on manual downloads. Second, it transforms those raw documents into a structured, searchable knowledge base. Instead of treating PDFs as blobs, we break them into clean text chunks with metadata. Third, it exposes a Q&A API. So a user can send a question like what does country X say about loss and damage and get an answer generated by the model but backed by the retrieval document segments. So this is built around a classic retrieval augmented generation or RAG design. So coming to the high-level system overview of this RAG architecture, at a high level, the system is split into two phases: the offline data pipeline, which is responsible for all the heavy lifting like scraping, downloading, extracting, cleaning, and embedding the PDFs. The result is stored in a Chroma vector database. The online serving layer is that is lightweight. It runs as a fast API service that, given a user query, retrieves the most relevant document chunks from the vector store, then calls a local LLM like Llama 3.2 through Olama to generate a grounded answer. And I've used Olama for this solution because I'm running it on my CPU and I wanted really a lightweight model uh, that can generate responses based on the questions asked. So separating these phases is important. Indexing is expensive but happens once in a while. Query answering needs to be fast and responsive, so that part is kept as lean as possible. So coming to the configuration and environment, so we have a separate environmental file that has all the key variables like FFD4 URL, persist directory, embedding model, and the LLM model. So coming to like the brief overview of the offline data pipeline and the online data pipeline. So this indexing phase. So now let's look more closely at the offline indexing pipeline, which prepares a knowledge base. So first it collects the PDFs links, then it downloads and extracts the PDFs with retrail logic, so transient network issues don't kill the run. Then we have clean and normalized. The raw text often contains headers, footers, page numbers, and odd white space. So these are all stripped out so that the embeddings capture more semantic content and less noise. The fourth step is building document objects. The clean text is wrapped into LangChain document objects. Then we have the persist chroma store. These documents are then converted into vector embeddings using the specified sentence transformer model. So after this phase completes, we effectively have a climate policy knowledge base that we can query semantically. So the next comes the question answering API. So on top of that index, the project provides a simple fast API service to expose the AI climate policy analyzer. So this API has a root endpoint for health checks and an ask endpoint where clients can post a question. So coming to the technology stack, these are all the various technologies that has been used in this climate policy analyzer. So here's a quick snapshot of the technology stack behind the system. Uh, then we have limitations and future work. So even though the system works end to end, there are several clear limitations and areas for future work. The first one is coverage. So right now the crawler indexes only about 50 PDFs. So it can be expanded for more comprehensive coverage. So the second one is citations and transparency. The current prototype focuses on retrieving relevant chunks and generating answers, but it does not yet display explicit citations or references back to specific pages. So adding those would be like really helpful for improving trust and verifiability. The next we have evaluation. So I have done evaluation only offline. Uh, so I have captured all the questions and their relevant responses from the API. Then I did manually using LLM as a judge, and then try to evaluate it based on three different parameters like relevance, accuracy, and correctness. So I would like to add this evaluation part into the main architecture framework so that it's very automated and planned. Next, we have advanced analytics. So beyond simple Q&A, the same index could power thematic summaries, topic clustering, or keyword maps across countries or themes. So the last one is user interface. So currently the interaction is via an API. Maybe it's like maybe the policy practitioners may find it not comfortable calling APIs directly. So that's why I would like to build a lightweight web front end that would make the practitioners to easily ask questions and easily accessible. So here is a quick snapshot of the API. So you'll have a request body where we can ask questions. Like here I have asked which financial institutions or coalitions are leading climate finance efforts. And then we have like a response body where we get the responses based on it queried from all those different PDFs. So here we got the answer of the financial institutions and coalitions leading climate finance efforts include N1, that is Green Climate Fund. Then we have N2 as Climate Investment Funds. We can also improve all these different responses based on prompt engineering as well. So when we are like typing a query, we can give a one shot prompting or two shot prompting, and also like chain prompting, or else we can ask like order it based on like different countries, order it based on different dates that they have implemented. So this can be really customizable. And coming to the evaluation that I did offline, here is a quick snapshot of the Excel file that I've used to evaluate it. And again, this is on the left hand side, you can see all the different questions and the answer that I got from the model. And I also gave like a brief context to the model so that it can be able to evaluate it based on accuracy, relevance, and clarity. So far, I have gotten like high accuracy, high relevance, and high clarity based on the model. Uh, uh, Maybe in the future when we are bringing in more PDFs, the evaluation can go more complex, and we may need an automatic evaluation process in the part of the architecture. So coming to the conclusion, so this AI climate policy analyzer is an end-to-end RAG system focused specifically on climate finance policy documents. It automates collecting PDFs from the UN FFD4 site, processing and converting them into a vectorized knowledge base, and serving a document-grounded Q&A API powered by a local LLM. And also this climate policy analyzer, this API is like really flexible. Not only it can work for this climate policy documents, it can work for like any documents that is searchable through web. So you just have to like modify or like swap the URL that I have in the environment file, and then replace it with a link, with the website link. And this model would be able to work perfectly fine for whatever domains that we wanted to ask questions and get answers from. Thank you so much for listening until the end of this video. Thank you.